Picture this. You lower a pocket watch toward a black hole. Carefully, slowly. Through your telescope, you observe its second hand. Tick, tick, tick. But as it approaches a certain radius, the so-called event horizon, something deeply strange occurs. The ticking slows. The second hand takes 2 of your seconds to advance, then 5, then a minute, then an hour. At the very moment the watch should cross this horizon, time itself appears to freeze. The watch hangs there, motionless, for eternity. And yet, and I assure you this is not a contradiction, if you were traveling with that watch, riding it down, you would experience nothing unusual. Your heart beats normally. The watch ticks at 1 second per second. And you cross that horizon in finite time. Same event, frozen from one perspective, completed in another. A student in the back protests, "That's impossible." No, my friend, that is relativity. And today I will show you why both descriptions are mathematically correct, and what this teaches us about the most extreme objects permitted by the geometry of spacetime. Takeaway: the horizon paradox is real, not a mathematical error, and resolving it will teach us what black holes truly are. Before we can understand black holes, we must understand why Isaac Newton, brilliant as he was, felt uneasy about his own theory. Newton told us, "This apple and the earth attract each other through gravity, as though the influence were instantaneous." In that Newtonian picture, if the sun vanished right now, poof, the earth would fly off its orbit at once, long before we saw the sun's light fade in the sky. Newton himself called action at a distance through empty space an absurdity. Yet he had no better answer. Neither did anyone else for 200 years. I spent a decade after special relativity asking, what mediates gravity? What carries the message from one mass to another? And the answer, when it finally came, was radical. No messenger is required. Mass does not reach across space to pull on distant objects. Instead, mass curves the space-time immediately around it. That curved region influences the region next to it, and so on. A continuous field. A planet does not orbit the Sun because the Sun tugs on it across a void. The planet orbits because it moves through curved space-time created by the Sun, locally. No action at a distance required. Mathematically, I write this relationship on the board in my field equation. On one side, curvature, on the other, matter and energy. Tell me where the energy is, and I will tell you how space-time bends. It looks like one equation. It is actually a family of coupled nonlinear differential equations. Solving them is non-trivial. Takeaway: gravity is geometry. To understand black holes, we must learn to think in curved spacetime. To see what curved spacetime means, we need a tool. Hermann Minkowski showed us how to visualize the logic of relativity with a simple diagram. Imagine you are here, one event in spacetime. A flash of light occurs at this moment. Light spreads outward at speed c. Where can that light reach in the future? Draw it and you obtain a cone, your future light cone. Everything you can influence, even in principle, lies inside it. And draw the reverse and you have your past light cone. Everything that could have influenced you up to now. In flat spacetime, far from any mass, these cones look the same everywhere. Light rays always make the same angle. That is our convention, and it is our compass. But near a massive object, spacetime is curved. Watch what happens to the light cones as you approach an event horizon. They narrow, they tilt. The future possibilities, where you can go, become more and more constrained. And at the horizon, something decisive occurs. Every future-directed path that stays slower than light points inward. Not because a hand reaches out and pulls you, but because the geometry itself has changed. Inward has become the direction the future leads. Takeaway: light cones show what is physically possible. Near a black hole, the set of possible futures is reshaped. Now let us make this concrete with a signal experiment. Light. Count it like the beats of a metronome. Imagine a lamp falling toward the horizon. Every second, by the lamp's own clock, it emits a brief blue flash. A distant astronomer watches through a telescope. Flash 1, flash 2, flash 3, flash 4, each emitted 1 second apart as measured by the falling lamp. What does the astronomer see? Each successive flash must climb out through more strongly curved spacetime to reach her. So the flashes arrive more and more slowly. The lamp appears to slow down. And more, as each photon climbs upward, it loses energy. Blue becomes green, then yellow, then red. This is gravitational redshift. Gravity is not a force here, but the geometry that determines how light's frequency changes along its path. As the lamp nears the horizon, the astronomer might receive 1 flash per minute, then 1 per hour, then 1 per year. In the idealized description of a non-rotating black hole, the flash emitted ever closer to the horizon arrives ever later. The intervals stretch without bound. The lamp fades, not because the lamp stops, but because its signals are delayed and redshifted until they slip beyond detection. But the lamp's own clock never stops. To someone falling with it, 1 second still passes per second. The horizon is crossed in finite proper time. Same event, 2 descriptions, both correct. Takeaway: distant observers can see a fall freeze through time dilation and redshift, while the infalling observer experiences an ordinary passage of time. Let me tell you a story. The year is 1915. Europe is at war. I have just published my field equations, but I cannot find an exact solution even for the simplest case, a single, non-rotating mass in otherwise empty space. Then I receive a letter from the Eastern Front, from Karl Schwarzschild, an astrophysicist serving in the German army, calculating artillery trajectories. He writes, in essence, the war treated him kindly enough, despite heavy gunfire, to take a walk in the land of my ideas. Between artillery calculations, Schwarzschild solved my equations. On the board, I write his result, the Schwarzschild metric. It tells you how spacetime is curved outside a spherical, non-rotating mass. Far away, the curvature fades and spacetime becomes nearly flat, as it must. But look closer and the mathematics seems to produce two singularities. At the center, at radius r equals 0, the curvature blows up. This is not merely awkward algebra. In this idealized solution, tidal effects grow without bound. The theory predicts its own breakdown. And then there is a second trouble spot. At a particular radius, now called the Schwarzschild radius. Compress enough mass inside this radius, and light emitted outward cannot escape to infinity. I write that radius plainly. R sub s equals 2gm over c squared. For the Sun, it is about 3 kilometers. For the Earth, about 9 millimeters. At first glance, the metric appears to misbehave at r equals r sub s. It looks like a singularity in empty space. Many physicists, including myself, suspected this must be a sign that nature forbids such objects. How could so much mass compress into so small a region? We were about to find out. Takeaway: Schwarzschild's solution revealed the event horizon and also tempted us with a singularity that, as we shall see, is not a physical tear in spacetime. What happens when a star dies? During its life, a star is a balance. Gravity pulls inward, while radiation pressure from nuclear fusion pushes outward. But when the fuel is exhausted, that outward pressure weakens. Gravity gains the advantage and the star collapses. How far? In the 1920s, physicists realized a quantum rule could halt the collapse. Pauli's exclusion principle tells us that electrons cannot all pile into the same state. Squeeze matter tighter and you must force electrons into higher and higher momentum states. Heisenberg's uncertainty principle gives the same flavor. Confine a particle's position and its momentum becomes more uncertain, typically larger. The electrons jiggle faster, and that agitation produces an outward pressure, electron degeneracy pressure. The star can settle as a white dwarf, remarkably dense yet stable. Astronomers had even observed such objects. Sirius B is a famous example. Problem solved? Not quite. In 1930, a young Subramanian Chandrasekhar crossed the sea to England and did a calculation that made many uncomfortable. Electrons can be driven to higher momentum, yes, but relativity imposes a ceiling. They cannot exceed the speed of light. That places a limit on electron degeneracy pressure. I write his result as a number, about 1.4 times the mass of the Sun. Above this Chandrasekhar limit, electron degeneracy pressure cannot hold the star up. Arthur Eddington, one of the most celebrated scientists of the era, mocked the conclusion. He insisted there must be a law of nature to prevent such absurd collapse. But nature is not obliged to protect our sensibilities. Heavier stars can collapse beyond the white dwarf stage. Under immense pressure, electrons and protons combine to form neutrons, and the star becomes a neutron star. Neutrons are also fermions, and their degeneracy pressure is stronger. Yet even neutron stars have a limit. In the late 1930s, Oppenheimer and Volkoff showed that above a few solar masses, neutron degeneracy pressure can fail as well. And then, nothing remains to stop the collapse. Takeaway: quantum rules can resist gravity until mass wins. For the heaviest stars, collapse can proceed beyond every known support. There was still a puzzle. If stars can truly collapse into black holes, why does the Schwarzschild description seem to say that nothing ever crosses the horizon? In those original coordinates, natural for a distant observer, the infalling object approaches the horizon and, according to the distant clock, takes an infinite time to arrive. Light signals sent outward arrive later and later. The picture looks like eternal hovering. I looked at that and wondered, perhaps black holes cannot form after all. But here is what I missed. Coordinates are a map, not the territory. When you project a curved surface onto a flat sheet, distortions appear. Some distort angles, others distort sizes. The physical Earth does not change, only the representation. Schwarzschild chose coordinates tied to clocks far away and to a radial label measured from the center. Useful, sensible, and yet, at the horizon, those coordinates become pathological. They stretch the distant time coordinate in a way that makes the horizon look like a tear in the mathematics. Choose a better coordinate system, one that does not freeze at the horizon, and the singularity at r equals r sub s disappears. The horizon becomes an ordinary place locally. No infinite curvature, no physical wall. What remains is the causal fact. Once you cross, you cannot send light outward to infinity. The true singularity at r equals 0 is different. It persists in every description. Takeaway: the horizon's blow-up is a coordinate mirage. The horizon is real as a causal boundary, but it is not a place where physics itself becomes infinite. Now we can resolve the paradox once and for all. The distant observer measures time with her clock, coordinate time. In that measure, the watch takes forever to reach the horizon. But the watch carries its own time along its path, proper time, the time you actually experience. And along the watch's own world line, the time to cross the horizon is finite, seconds or minutes depending on the black hole's mass. Both descriptions are correct because they measure different things. It is like asking for a distance. The straight line between two cities is one number, the winding road is another. Neither contradicts the other. They refer to different measures. Locally, at the horizon, nothing magical happens. Space-time curvature there is finite, and for a sufficiently massive black hole, the tidal forces at the horizon can even be gentle. But once across, the light cones point inward. Inside the horizon, Outward is no longer a future direction. The watch's future contains only the central singularity. In that sense, the singularity is not merely a location you might choose to avoid. Inside the horizon, it is an event in your future, a final moment toward which every time-like path must go. To an outside observer, the watch never quite crosses. It freezes and fades. To the watch itself, it crosses in finite time and moves inevitably toward its end. Both are true. There is no contradiction. Takeaway: proper time and coordinate time answer different questions. Distinguish them and the horizon paradox dissolves. Schwarzschild's solution describes a perfectly spherical, non-rotating black hole. But every star in the universe rotates. Angular momentum is conserved. So every real black hole must rotate. For decades, no one could solve the field equations for a rotating mass in closed form. Then, in 1963, Roy Kerr succeeded. I will spare you the full expression. What matters is the geometry it implies. Rotation breaks perfect spherical symmetry. Space-time is dragged around with the black hole, frame dragging. Near enough, you cannot remain still relative to distant stars. The geometry itself carries you. There is a region called the ergosphere, where this becomes unavoidable. Inside it, you may still escape, but you cannot hover. Deeper in, you meet the outer event horizon, the point of no return. And in the ideal Kerr solution, there is even an inner horizon. Beyond that inner horizon, the mathematics opens into stranger territory. The central singularity is no longer a point, but a ring. And there appear to be paths that avoid it, leading, in the maximally extended solution, to other regions that resemble other universes. Now, I must put a bright warning on the board. These are mathematical extensions of an eternal, perfectly clean solution, a black hole that exists forever in an otherwise empty universe. Real black holes form from collapse and are fed by surrounding matter and radiation. When you include realistic disturbances, many physicists expect the inner horizon to be unstable, perhaps becoming a destructive region that seals off the exotic extensions. Takeaway: rotation enriches black hole geometry, but the most exotic interior passages may be artifacts of idealization, not features of nature. Let me tell you what is possible, purely mathematically, in the maximal extension of these solutions. In the complete Schwarzschild geometry, there is not only a black hole region where things fall in, but also a white hole region where things emerge. A white hole is the time reverse of a black hole, a horizon you cannot enter from outside. In that maximal extension, there are also two separate exterior regions, two universes if you like, connected by an Einstein-Rosen bridge, a wormhole. Could you travel through it? In the eternal solution, no. The bridge is not a stable tunnel you can traverse at leisure. Its geometry pinches in a way that prevents any slow traveler from crossing. To hold open a traversable wormhole, theorists find you would need exotic matter with negative energy density. Classical forms of matter do not behave this way. Quantum physics can produce tiny, fleeting negative energies. But whether nature can provide enough to hold a macroscopic wormhole open is unknown. More importantly, real black holes are not eternal. They form from collapsing stars. The white hole region and the second exterior region are relics of the eternal idealization, not something a collapsing star is expected to create. Takeaway: white holes and traversable wormholes are elegant possibilities in the equations, but they are unlikely to be realized by realistic gravitational collapse. So what is real? The central singularity at r equals 0 is not a coordinate artifact. It remains in every description of the Schwarzschild solution. In that idealized mathematics, curvature grows without bound and tidal forces diverge. General relativity signals its own limit. But what is a singularity really? In a Penrose diagram, the singularity is not drawn as a point in space you might walk around. It appears as a boundary of the future. For anything inside the horizon, it functions as a when, a final moment that cannot be avoided. And this is the crucial lesson. Our theory, magnificent as it is, does not tell us what happens there. At the singularity, we expect quantum physics to matter, and we do not yet possess a complete theory of quantum gravity. Takeaway: the singularity is where general relativity admits honestly, here my predictions end. Now let us return to where we began. The watch falls toward the horizon. To you, the distant observer, it appears to slow, freeze, and fade. To the watch, nothing unusual happens at the crossing. It crosses in finite proper time. For 2 centuries, we imagined space and time as absolute, identical for all. Relativity taught us otherwise. Time depends on your path through space-time, on motion and on curvature. Near a black hole, this difference becomes extreme. But it is not a contradiction. It is the nature of space-time. The horizon is not a place where time stops. It is a boundary in causal structure, a point of no return defined by what light can and cannot do. Cross it, and your future contains only one destination in the classical picture, the singularity. Black holes, meanwhile, are not merely speculation. We infer them from the motions of stars around invisible companions and from violent cosmic events that betray immense compact masses. White holes, wormholes, parallel universes? These remain for now largely the province of beautiful mathematics and cautious skepticism. And yet, nature has surprised us before. We once thought black holes themselves were absurd. The universe is under no obligation to soothe our intuition, but it does obey its laws. If we are patient and brave, the mathematics will show us what is possible. So, the watch crosses, and from far away, it never seems to cross. Both are true. And that is the gift of relativity, to teach us that reality is richer, stranger, and more beautiful than we imagined.